In section 8.2, we're learning a new integration technique that's useful for dealing with products when we can't use like an unchained rule or some other technique that we already know. There is no sheet to go with this video, so you'll just need to be ready to take notes in your binder. We're going to be doing this example up here real soon, and I just want to point out that while this looks like we might be able to use the unchained rule, we really can't, because we have e to the 3x, and then we have times x dx, and that x is a problem, right? Because our inside function is really 3x, and its derivative is just 3. So we can't use the unchained rule. So you might then think, well, why don't we let's just use U-substitution. Let's let u equal 3x. That would give us what? That du equals, well, let's see, du dx equals 3. So du equals 3 dx, and therefore 1/3 du equals dx. And we could try to substitute over here. See, I'll change colors, so I would have just e to the u, and now I could replace the x up here with 1/3 u, or u over 3, and we already figured out that we can replace the dx with 1/3 du. Alright, which would give us 1/9 times the antiderivative of e to the u times u du. And you see, I still have the same problem I had before. I've got that variable there. I can't unchain this, so we can't even use U-substitution here. It's just not going to work. So let's take a look at what we have here. We're going to use the product rule here to help us come up with another way of taking an antiderivative. So you might recall the product rule is just our first function times the derivative of our second plus the derivative of the first times the second. I think I usually wrote it in a different order, but this still works. All right, or so we might say it's u times v prime plus u prime times v. All right, and I'm going to turn it around just a little bit so that it's u times v prime plus v times u prime. All right, just switching the u prime and the v there. No problem there. All right, well, if the derivative of this equals what we have over on the right side, then of course it makes sense that if we take the antiderivative of what we have on the right side, we will get u times v. So that's what we're writing here. The antiderivative of all this would equal u times v. All right, and since we have a sum here, we can split this antiderivative up. So that's what we're doing there, just distributing the antiderivative. All right. Now, before we move to the next slide, let's just establish a couple things. I'll even draw little arrows here, but we know that dv dx is equal to v prime, and that du dx is equal to u prime. All right, so I've written that out over here, and that of course would mean that dv is equal to v prime dx, and du is equal to u prime dx. Let's start from there on the next slide. So these were the last lines that we had written on the previous slide. And all we're going to do here is replace our v prime dx with dv, and we'll replace the u prime dx with du. So what we end up with is that u times v is equal to the integral of u dv plus the integral of v du. And therefore, we would have that u times v minus the integral of v du. So just bring this integral over to the other side, that would equal the integral of u dv. And if we just turn that around, we have that the integral of function u with respect to v is equal to u times v minus the integral of v du. That seems confusing, but just bear with us here. It'll help when we do an example. If you're ever on Whipple Hill and you go to the topics page and look at the chapter 8 topic, you'll see I put a little picture in there that kind of looks like this, that kind of shows this idea. Even though these aren't definite integrals, this is maybe a way we can kind of picture this working. So the blue, of course, would be v du, or in other words, the area between this curve right here and the u-axis, whereas the red would be the UDV, the area between the curve and the v-axis. And if you add those two areas together, then you get the product of u times v, which of course is the area of the rectangle. I kind of thought that was a nice way to somewhat picture this, or give it a geometric meaning. So this is the part that you need to make sure you have in your notes. All right, this is what we call integration by parts, and it says that if u and v are functions of x and have continuous derivatives, then the integral of u with respect to v is equal to u times v minus the integral of v with respect to u. Let's now see how we apply this to an example. So here we have the example we were looking at before. And what we need to do, okay, this piece of the rule is the integral we're starting with. And we need to figure out which of this integrand that we have here is going to be the u and what's going to be the dv. What you want the u to be is some function that you can take the derivative of it. So I'm going to let u, okay, equal x. And then everything else that's in your integrand needs to be the dv. All right, so we're going to say that e to the 3x dx, you got to include the dx also, is equal to dv. What we need to do now is figure out any of these other parts that we don't have. Now we already know what u is, so we're good there. I don't believe we know what v is. We need to figure that out. And once we do that, we'll have that piece. We also need to figure out what du is. All right, now du won't be hard. We know that du dx is equal to 1, so therefore in this case du equals dx. Don't assume that that will happen every time. Now over on the other end here, we need to figure out what v is. We know dv. So of course to go from dv to v, we just need to integrate. So we'll integrate, basically we're integrating 1 times dv, and that will give us v. And so we need to also integrate e to the 3x dx. All right, well, let's see, we can do that by using a pretty quick unchain rule, right? We can multiply the dx by the 3, because that's the derivative of our inside function. We'll compensate with a 1/3 out here. So it looks like v is equal to 1/3 times e to the 3x, right? The 3 dx drops, right? We're just dealing with the outside function, which is e to a power, and that's just itself. And we have a 1/3 in front. So now we know what every piece is over here. We know what u is, we know what v is. Once again, we have v, and then we also know what du is. So it's time to kind of do some substituting in here. I think I'm going to change colors now. So we've gone into a new phase here. So we have that the integral of x times e to the 3x dx is going to equal my u times my v. All right, well, u is equal to x, and let's see, v is equal to 1/3 e to the 3x. So I'm just going to multiply those, and then we have minus the integral, and we need v again, so we've got our 1/3 e to the 3x, and then we need our du, and du is equal to dx. So we've now put our equation in, and all we have to do to end up getting our answer is do the antiderivative one more time over here with this. So we got to get rid of that integral sign. So let's see, we're going to have, looks like 1/3 x times e to the 3x, and then we're going to have minus, we can bring that 1/3 out, and we've kind of done this already. To integrate e to the 3x, we need a 3 times the dx, and we'll compensate with another 1/3 out there. So let's see, I'll just bring my answer right up here now, and we're going to end up with our integral equaling 1/3 x times e to the 3x minus, and we will have 1/9, and I think we'll just end up with e to the 3x. All right, once again, taking care of that outside function, the 3dx just drops, and then we have our plus c. And now we're done. If you go to page 525 in your book, you'll see these guidelines for integration by parts. And there's two main things you're looking for. First of all, we want u to be the factor. Remember, this is usually done with a product, okay? That should be the factor of the integrand whose derivative becomes a simpler function. All right, in our example, we let u equal x, and of course when we took its derivative, we got 1, which was a simpler function. So, if you go down in degree, that's really a good thing for you to do. And then the other thing you look for, okay, is you always have to choose the dv to be a part of the integrand that can be integrated, all right, that you can take as integrals. So we did a wise choice when we had e to the 3x dx equal to dv, because we could take the antiderivative of e to the 3x without too much trouble. This process is going to take a little getting used to, so let's look at another example. I've included the guidelines as well as our rule at the top. You probably just want to get used to writing this rule out, at the top of the page. Just write it there, and that way you can follow it. All right, let's take a look at this example. Now, according to the guidelines, we should probably let u equal our x cubed, all right, because of course if we take its derivative, we'll get something simpler. But that would mean, let's think about that, that would mean that dv is going to end up equaling the natural log of x times natural log of x dx. And here's where the problem lies, okay? If we take the antiderivative, of both sides, we've got a little problem here. We haven't learned what the antiderivative of the natural log of x is. So this is going to hold us up here. We really can't do anything with this. So what should we do? Well, I'm going to first of all erase all this. Should have gotten a thicker eraser. And so if the method doesn't seem to be working, pretty much the only thing we can do is backtrack, and let's do something a little different, all right, with our u perhaps. Maybe we should have let u equal the natural log of x. All right, we can take the derivative of that, so that might work. And then we could let dv equal x cubed times dx. All right, and we can still take the antiderivative of that, so I think we're okay. All right, so we'll have that du dx, of course, is 1 over x, and therefore du is equal to 1 over x dx. And we can stop there, because if you look back up at our rule, we just needed to know what du was, okay? We don't need to solve for dx, we're not doing that kind of substituting. All right, now come over here to our dv, and of course if we integrate, we'll figure out what v is, and the integral of x cubed dx, of course, is just going to be 1/4 x to the 4th. All right, so let's try plugging in our u's and our dv's and v's and all that. So we're going to have, let's see, we need u times v, so we'll have the natural log of x times the 1/4 x to the 4th. All right, natural log of x times 1/4 x to the 4th. And then minus the integral of our v. So let's see, I think I'll just pull well, that's okay, I'll just write it in here. So 1/4 x to the 4th. And then we need our du, and our du was 1 over x dx, so times 1 over x dx. All right. So let's see, I might have enough room over here, so we're going to have 1/4 x to the 4th when we come up here, times, let's see, that's a 4th times the natural log of x. And then we'll have minus, let's bring that 1/4 out, and it looks like we'll just be left with x cubed dx, and we can take that integral. So let's see, x to the 4th over 4 times the natural log of x, and now this will be what, minus 1/4, and we'll have another 1/4 x to the 4th, and then plus c. So we'll clean that up. Actually, we could pull a 1/4 and x to the fourth out to the front. That might be a good thing to do. So if we do that, we'll be left with just the natural log of x. It looks like minus a fourth. And then we have our plus c out there. Alright, well that wasn't too bad. Just you have to be a little flexible. If it doesn't seem to be working one way, try it the other way. And that seemed to work a little better for us. I haven't been letting you really do much work here on your own, so why don't you try our method here on this problem. You can see there's no unchained rule we can do here. We just have a product, and so you need to decide which of these functions is going to be u and which is going to be dv. Certainly hope you're already thinking that the x squared should be the u. That will turn into simpler derivatives. And we can take the integral of the sine x dx. So why don't you go ahead with that, pause the video, and if you get stuck, then start playing the video and I'll catch up to you. Alright, see if you got started in this way. Okay, so I let u just be the x squared, and we work it down, we get du is equal to 2x dx. So we're set there with our du. And now we have dv is sine x dx, so we take the antiderivative and we'll just have negative cosine x for v. So I have my u times my v minus, and then I've got my v times my du, right? And let's see, we can make that a little prettier by just bringing the negative out here, and then we would have a plus 2 times the antiderivative of x times cosine x dx. Perhaps you might have stopped here. If not, great, if you were able to keep going. But notice what we have now. We have another situation, another integral, where we need to use integration by parts. So we'd better get to it. Now, we're not going to lose this negative x squared cosine x. That's still there. And we'll still have a plus 2, but now we need to focus, focus our attention here now on this piece right here. And of course, let's go ahead and get started. We'll just let u equal x. Alright, so go with that and see what happens. Alright, check and see if you got this. Okay, so here we are going to let u be x. We can figure out pretty quickly that du equals dx, and then that means everything else is dv. We can take the integral of cosine pretty easily, and that'll give us sine of x. Alright, I kind of didn't show the integral in there, but we did the integral of cosine x dx. Alright, and so we have the x squared, negative x squared times cosine of x plus our 2, and now inside of that we'll have x times sine x, because that's our u times our v, and then minus the integral of sine x dx. I'm going to slide this slide up just a little bit so I get a little more room. We can finish writing our answer. Alright. So all I had left to do was to take the antiderivative of the sine of x, and that gave me negative cosine x. And then I just distributed my 2 across the brackets there. So we have our first term plus our 2x sine x, and then minus the 2 times the negative cosine x. So just clean that up and we have our answer. Before we move on, I would just like to point a couple of patterns out here. I'm going to slide this up just a little bit here. Notice that in our answer, what we first have is the product of our original u function, right, the x squared, times the antiderivative of the other piece, all right? And then we have the derivative of u, the 2x, times the antiderivative of that cosine. So we're back to sine. And then we have the derivative of the 2x, seems to keep going down in degrees, that would just be the 2, times the antiderivative of the sine. Alright, and what keeps happening also, one other thing you'll notice, we had a minus here, then a plus, and then a minus. Of course that ended up being a plus because of our antiderivative of sine of x, but it's kind of alternating the plus, the minus, the plus. We're going to seize upon those two patterns to find a quicker way maybe to do this problem, because it is a bit cumbersome when you set out to do integration by parts, and then within that integration by parts you find that you have to use integration by parts one more time. That's quite tedious. So let's see if we can find a shortcut here. Alright, this method is what we call the tabular method, as you can see here. It's still integration by parts, but it's a quick way to do integration by parts, especially when you know you're going to have to maybe do it 2 or 3 times. And that can happen sometimes when you've got a power function here that might have a cube or a 4th degree. This one even square, where we're having to do the integration by parts twice, as we saw on the previous slide. So what you do is you set it up. You've got 3 columns here. In this first column, you're just going to alternate the signs. We saw that pattern, that one term was plus, one term was minus. So and you always start with a positive. You go positive, minus, all right? And then in the middle column, you're going to have u and its derivatives, all right? So we decided that u was going to be x squared. That was a wise choice, and now we're going to take its derivatives. So we'll have x squared, then we'll have 2x, and then we'll have 2, and we could go one more, we'll have 0. Alright? And then over on the right hand side, we're going to have v prime and its antiderivative. So I'm just going to write the sine x. Okay? Understand, I'm not writing dv. dv would be sine x times dx. Let me show you that up here. So, if we have that dv equals sine x times dx, let's just divide over by the dx. That would give us dv dx equals sine of x. And of course dv dx is v prime. Alright, so that's all you need to start with. You don't need the dx there. But we are going to take the antiderivative of this. So let's see, antiderivative of sine x is going to be negative cosine x. Antiderivative of negative cosine x is going to be negative sine x, right? Because the antiderivative of cosine x is just sine x. And now the antiderivative of sine x, negative sine x, sorry, is going to be, we'll be back to positive cosine of x, right? So, now here's what you do. You might remember what we said. That first term consisted of just multiplying the u by the first antiderivative. So you're going to draw a straight line across, horizontal line across, and then a diagonal line down. Alright? And then we do the same thing here. Horizontal, diagonal down. Horizontal, diagonal down. And once we get to 0, there's nothing to connect it to, so we stop. Alright. And so what this tells us is our answer is going to be positive x squared times the negative cosine of x, alright, and then it's minus 2x times the negative sine of x, and then it's plus again the 2 times the cosine of x. And then we run out, it'll just be minus 0, so no sense there, and then we'll just put a plus c. So let's see if this is what we got before. Let's clean our answer up. We have negative x squared cosine of x plus 2x times the sine of x, and then plus 2 times the cosine of x plus c. I believe this is what we got before, so you can check that with what you wrote down, but that is our answer that we got. So that was a little quicker way to do it, and I encourage you, you could use this method on all of them if you like. It does work, even the ones where you don't have multiple times of having to do integration by parts. So leave that up to you. Page 530 has a nice little diagram talking about the common integrals where we can use integration by parts. Of course, we've seen a couple of examples where when you have the power function x to the n somewhere in front, that you can let that be u, and then if you have e to an exponent, or sine or cosine, then those are easy functions to take the antiderivative of, so you let those be dv. So that's a pretty common situation where we would use integration by parts. We saw an example over here, though, that it also works if you have the x to the n power, but if what you have in the dv is not something here that you could take the antiderivative, then we're going to let u be the natural log of x, okay, because that we can take the derivative of. All right. This would also work with arcsine or arctangent. You don't run into that situation too often, but remember we do know the derivative of arcsine and arctangent or any of the inverse trig functions. Now with functions where it's a product of the exponential, the base e with a sine or a cosine, apparently it does work better if you let u be the sine or the cosine part and let the dv be the e, the ax. Of course we can take integrals or derivatives of either of those, but apparently this works a little better. I guess we might see an example of that. I really like these problems, numbers 73 to 78. And the nice part of it is they're not actually asking you to take the integral, they're just asking you how would you do it, what rule would you use. So we just want to identify what would be the most appropriate rule for these situations here. Some of these you've seen before, some of these might be a little new and require integration by parts. Some of the possible answers you could give here is you might say, okay, this would require the unchained rule or U-Substitution. That could be a possibility. You might need to use integration by parts that we just learned. It might just be a basic integral, we have a basic rule for it, or there is one other option. I think there might be one or two on here where maybe it requires like an an inverse trig function. So I'll put that option there, inverse trig function. I guess we also have the natural log rule. I don't know if you can tell that, but that's ln, natural log rule. Pause the video and see what you think about each of these. Then we can go over it together. Well, first thing I would do is look for the ones where I can use the unchained rule. I think it's kind of interesting to compare numbers 77 and 78. One of these you can use the unchained rule on. The other one you cannot. If you look at number 78, we could rewrite that as x squared plus 1 to the negative 1/2 power, and we're left with a times x dx. Whereas over here, we would have the integral of just x plus 1 to the negative 1/2 times the x dx. So yeah, 78, we could go with unchained rule, right? But we can't do that with number 77. So we might need to come back and think about that one. Let's see. Are there any others up here where we can use the unchained rule? How about looking between numbers 75 and 76 here? I do believe one of these we could use the unchained rule with. They look kind of similar. Of course, our inside function is going to be the exponent. So over here it would be the x squared. So it looks to me like, yes, we would have its derivative, right? We've got 2x sitting right there. That could be times the dx. So this would be another unchained rule that we could do. But over here we can't do that, right? Our derivative of 2x is just 2, and we're left with an x squared. All right, it looks to me like this would be a prime candidate for integration by parts, right? So I'm just going to write parts right next to it, because we could let our u be x squared and our e to the 2x dx be our dv. Alright, coming up to the top 73 and 74, this is another situation where one of these, I believe, we could use the unchained rule with. It's a little sneaky, though. But if we rewrite number 73 as the natural log of x, and then we've got times 1 over x dx, hopefully you're recognizing that 1 over x, right, is the derivative of natural log. So it'd be nice if natural log was an inside function. So I'm just going to make it an inside function. And of course its outside function would be to the first power. So there we go. There's another unchain. Put that out here. Unchain rule that we could do here. Over on this one though, I think this is one that we've already did on this video, right? This would be integration by parts, where we could let the u be the natural log of x, and we could let the dv be the x dx. All right. Now, if we look, we never did come up with an answer for number 77. Notice, I don't think we can use integration by parts on that one because we really don't have a product. What we have is a quotient. You might be thinking maybe this one is an inverse trig function, but I actually misled you a little bit. We don't have, I believe with the inverse trig functions we need like an x squared inside the square root, and we would just have a 1 over it, something like that. This one actually would be a U-Substitution one. Remember, that was another, if we couldn't use unchain rule, we would look to use U-Substitution, and I forgot to list that here, but we'll put that U-Subst. Alright, if you think about it, if you let u be the x plus 1, then you can also, you can end up replacing that with the u, but then you can also replace the x with something and then be able to distribute. You'll have u the negative 1/2 and you can distribute that. So it'll work out if we use U-Substitution. That was a little tricky. I want to strongly suggest that you take a look at examples 3, 4, and 5. I considered putting them on this video, but I knew it would really make it too long, so I did not do that. We might, if we have time, we might take a look at these 3 examples in class.